Alright guys, today we are jumping into 3.8, which is over graphing polynomials, okay? So I will tell you that this section can be a little bit tricky, which is why it's really important that you buckle down and you know how to decipher these, how to tell them apart, okay? And then knowing which qualities make the graphs look a certain way. So just make sure that you're paying attention, especially to these first couple of charts. And if you are, then you should be fine. I'm not too worried, okay? So we'll start off just by classifying these. So when we say degree, what we mean is just like the highest exponent that's in the equation. So if you look at this first one, there's no exponent, right? There's not even any variables. It's just y equals 3. So our degree would be 0, okay? The name of this, we just call that a constant. Anything that doesn't have a variable with it, it's just a constant. Okay. Now we have y equals 3x plus 4. We can see that we have an x, okay, that's our variable. It's to the first power, so that degree would be 1. We would call this linear, because if we graph this, it would just be a straight line, okay? We then have y equals 3x squared plus 5x plus 1, okay, getting a little lengthier here. We can see that our highest exponent is 2, so that is our degree. And we would call this quadratic. We know how to graph those by now. Okay, and then we have 3x to the third, so the third power is our highest degree, so we'll put 3 there. We call these cubic functions. Okay, and then we get down to degrees of 4, degrees of 5. These are just polynomials that are bigger. I'm not even going to name them because it's not super important right now. But just know that the highest exponent in that equation, that's your degree, okay? Sometimes when you get into like your upper level algebra, college algebra classes that you might be in, your professor one day might like give you this equation, but maybe mix it all up, okay? So know that if it's not in order from descending exponents, that you might have to put it in order. I'm not going to do that to you, but just know that that is a thing, okay? So then we have, what do these polynomials look like when they're graphed? Okay, so we know what a constant looks like. For instance, our above example was y equals 3. Okay, if we graph that, it would be a horizontal line through the point 3 on our y-axis. It would look something like that. Does that cross my x-axis? No. Okay, didn't we say it had a degree of 0? Yeah, so make note of that. So if it has a degree of 0, it doesn't cross your x-axis. Now we have a linear line, so we'll use the same one, y equals 3x plus 4. I'm just gonna like rough sketch that. Okay, does that cross your x-axis? One time, right? And what was the degree? 1. I'm sensing a pattern. Let's say that I had y equals x squared minus 2. Looks something like this. How many times did that cross my x-axis? 2 times, okay? And then let's say we had y equals x to the third. Well, if I had something like that, we've graphed those before as well, it would look kind of like this, okay? And I can't really tell if that crosses my x-axis. I know that it does. I know it crosses 3 times, but sometimes it's a little bit hard to tell, okay? But also just know that that degree, that's the possibility. So just how many times it can possibly cross the x-axis. It won't always be like that. So for instance, if this was y equals x squared plus 2, which don't write this, but just show you this. This would be that u. Okay, does that cross the x-axis? No, it doesn't, but if I shifted it down, it would still be the same shape, and it would, okay? So know that, and I want you to write this over to the side, that degree, it just equals how many times your graph will possibly, and I'm going to underline that and put it in all caps because that's important, will possibly cross your x-axis. So again, it's just the possibility, okay? So moving forward, we've got our in behaviors, which is going to be a big thing for today, okay? And it's super important that we memorize these, that we know what these look like, okay? This chart that we're about to draw here. But basically what this means is if I look at the graph, and we've talked about this before, as x goes to one side, so as x goes to the right in this case, which would be approaching infinity, where's y going? Okay, same thing down here. As x goes to the left, to negative infinity, where the heck is y going? Okay, what it tells us to do is to place these graphs in Desmos and then just determine what that end behavior is going to look like. So I'm going to go ahead and do that. Okay, so literally all I did was I typed in that first equation into Desmos, and I told you guys we are going to be using that website here coming up in the next couple units. Okay, it'll be after Christmas break, but we do want to get familiar with that website because it's on the EOC and we can use that, so we're going to definitely learn how to type those in. But it's really easy. All I did was type that equation exactly as it reads into the graphing calculator, and it just graphed that for me. Okay, so we're going to fill out this chart next. This is super important. This is something that you will need to know, okay? We'll have to memorize this. It'll be pretty easy to memorize once you start practicing these, so I'm not too worried about it. But if we look, let's just look at this example that we have here. So my equation is 4x to the fourth plus 6x to the third minus x. So let's just look at our degree, which is 4, right? Because 4 is the highest exponent, okay? Is 4 even or odd? Even, right? Hopefully you knew that one, okay? So the 4 is even, and then we look at our leading coefficient, okay, which is just the number in front of that variable with the exponent, which is also a 4. And is that 4 negative or positive? Well, we can see there's no negative sign in front of it. It is a positive 4. So therefore, what we have going on is going to fit right inside this first box. We've got an even degree, we've got a positive leading coefficient. So now what I need to do, okay, is figure out what's this graph doing. Okay, so if we look, we've talked about our limits before, which is basically all that this is. So first off, as x is going to infinity, so as x is going right, what is y doing? We can see that y is going up to positive infinity. Okay, same thing with as x is going to the left, okay, y is going up. We can see that, okay? It's the same concept as our limits that we've already dealt with, okay? Why is this important? Why do I need to know this? Well, now I know that this is going to relate to the degree of my polynomial and to whether or not that coefficient is positive or negative. Okay, so if we look, this is going to be the same case for all of them. As we go to the left, if we have an even degree and a positive leading coefficient, we're going to rise. Okay? Same thing for if we go right, we're also going to rise. Okay? So we could write it in this notation if we wanted to. It's fine if we do, okay? But we'll just shorten it by saying if we go left, we're rising. If we go right, we're also rising. Okay, so what that would look like on a graph, just like what we have here above, it would look like this, okay? And let me just clean this up a little bit. Okay, so now let's go ahead, and just for time's sake, I'm not going to graph that next one. If you want to go to Desmos and type that in, that's totally fine. But with the positive leading coefficient, if we change that to an odd degree, so instead of even, it's going to be odd. If we look, our left is now going to be falling instead, okay? And our right is still going to be rising. And we've kind of seen that already with whenever we graphed those cubic functions, right? So whenever we graphed that y equals x to the third, okay, and it went like this, well, that had an positive leading coefficient, right, and an odd degree, so it made sense that to the left it was falling, to the right it was rising. And then if we flip that around, if we make that a negative x to the third now, so instead of being a positive leading coefficient, it's now negative. It's still going to be an odd degree though, right? We're now doing this. It's kind of a bad graph, but either way, the left is now rising and the right falling. Okay, same thing for if we change the coefficient on an even degree, just like if I had a u, right, that was going up both directions, and I made it a negative x squared, it would flip down. So I know that to the left I'm going, or I'm falling, and to the right I'm also falling. Okay, so this little chart, honestly, if you can't memorize things, if you've just kind of reached your max on memorization, just draw your u's and your just basic cubic functions, okay? So I know that this is x squared, negative x squared, x to the third, negative x to the third, okay? So if you need to draw that, go ahead and do it. But we should always know that based on the degree and our leading coefficient, I'm just going to call it LC just because my blank is small, but make sure you know that that's leading coefficient. If you need to write that, I guess I'll write it out. Those are going to tell us what direction that our polynomial is going, okay? So make sure we're good on that chart. Now we're going to talk about what multiplicity, hard one to say, what this means. So basically what this is it's the degree that tells you how your value moves through the x-axis. So if you have an odd multiplicity, then the line is going to cross through that x-axis. And if it's even, then it's going to bounce. It's going to bounce that x-axis, okay? So what I mean by this, like for instance, if I just had like a linear equation, like just a line, okay, we can see that I totally just crossed that x-axis. Okay, it went straight through. Okay, but now let's look at, for instance, we'll go back to our u's, okay, so those quadratics, I know you guys love them, okay? Let's say that, for instance, we have this. Okay, this is what I would call a bounce, see? So I definitely hit that x-axis, but I didn't necessarily cross it. I didn't go to the other side, okay? I just kind of bounced on top of it, okay? So that is what multiplicity means, and we'll talk about that. We're going to do an example here in the next slide. Okay, so given the following polynomial, it wants us to solve it, then graph it. It's important to do it in that order because you're not going to know how to graph this if you haven't tried to solve it out. Okay, so we'll look. Y equals x to the third minus 6x squared plus 9x. We know the first step is always just change that y to a 0. And then always check for a GCF. And if I look, I do have one on this. It is just going to be x. And when I pull that out, it leaves me with this equation. Okay, so now I've got to try to x method that inside part. And if I look, 1 times 9 is 9. That's going on top. Two things that will multiply to 9 that will add to negative 6. Think about it. -3 and -3 will work. So 0 is going to equal x times x squared minus 3x plus 9. And then we group these together. First two terms have an x in common. Next two terms have a -3 in common. Rewrite, make sure I keep my GCF. And this is what I end up with. So we know that we set each factor equal to 0, right? And that gives us what our x values are. So if I look, I end up with x equaling 0 and 3, but I actually end up with 2 3s. So technically this has a multiplicity, we'll abbreviate, of 2. Okay, so I have 1 0, so that's just a multiplicity of 1. Okay, and then I have 2 3s, which is a multiplicity of 2. Okay, and what I'm going to do, this graph is not going to be perfect. Okay, it's not even going to be that pretty. It's just going to be a rough sketch of what this is going to look like. Okay, we'll get into the prettier graphing in in the next section, but we won't cover that today. So if I look, I know that these are x-intercepts. If I wanted to write them like this, I could. Okay, I don't necessarily have to. I just know that one's on 0 and one's on 3. Okay. Then I'm going to look at my end behaviors, and I can go back to my chart if I need to. I know that I have a positive leading coefficient because this is a positive 1. So positive, and I know that it is odd. So I need to look at what that is. So a positive coefficient, odd degree, means that my left is falling and my right is rising. So I'm just going to go ahead and put those arrows there just so I know that this is where I'm coming in and where I'm going out on this graph. Okay? And then I want to look. So if my multiplicity is 1 for that 0, that means I'm going through it. Okay? So I know that this is coming up. 0 is the first thing it's going to hit, and it's going to go all the way through. And then I know that I'm going to bounce on that 3, okay? Because it has a multiplicity of 2, and I know that if it's even, it's just going to bounce that and then go up. Okay? And that's it for this one. So not too crazy, okay? Just knowing those end behaviors and just knowing what the multiplicities are and how those work, okay? Cool. So now we're going to move right along here. So now we're going to talk about relative maximum and minimum. So these turning points, these are the points where the function switches directions, okay? So turning points define, is the function increasing or decreasing, okay? And if it changes from increasing to decreasing, that's a turning point, okay? So if it's higher than any nearby point, then that's what we're going to call a relative maximum. I'm going to abbreviate relative max. And then if it's lower than any point, that's what we call minimum. We've actually already talked about this, okay? So if we look at this graph that it's given me, I'm just going to use my highlighter here. So I know that this point would be a minimum, right? Because it's lower than all the other points. And this point would be a maximum. Now, you may be overthinking this, which I definitely don't want you to do that, because we definitely tend to do that in this class. But what you might be thinking is, why is this a maximum when this graph goes higher? Okay, that's why we call it a relative maximum, because relatively speaking, that's the highest point on my graph. I know that I am going all the way to infinity in both directions, okay? But relatively speaking, where is the maximum on this graph? Okay, and that's what we need to look at. So together though, these are going to be what we call extrema. You won't hear me say that a whole lot in this class, but that's definitely a term that college algebra teachers like to throw on a test, okay? So together the maximum and points, if they ask you for an extrema point, that's all that means. Is it a maximum? Is it a minimum? Okay? So now, what we're going to do, and this is like the main part of today that you've definitely got to be able to master, it's just going to be a point of practicing, is just to make some rough sketches, okay? I need to make that mark. Okay. So we'll start off, the first two things that it tells me, so the even degree and the positive leading coefficient, okay? These are going to tell me my end behaviors, so I've got to know both to know what this is going to do. And this is where my chart's going to come in handy. I don't care if you use the chart today, okay, because we're practicing. You'll eventually know that chart by heart, hopefully, and if not, you know how to draw your U's and your cubics that you can make that chart. So if we look, first off, even degree, positive leading coefficient. So if we look in the chart, even and positive means up to the left and up to the right. So I know that relatively speaking, this graph needs to have those directions here. So I'm going to draw those arrows, okay? Then what I want to look at is it's telling me my roots. So I have a root at -1 with a multiplicity of 2. Is 2 going to be a through or a bounce? Well, it's even, so it's definitely going to be a bounce. And I'm going to go ahead and put the dot at -1 because that's where the root is, okay? And then if we look, we've got another root at 0, so I can go ahead and make a dot at 0. Multiplicity of 1, so that means it's going through. And then a root at 5 with a multiplicity of 1, so also going through, but the root this time is going to be at 5. Then I have two imaginary solutions. We have not talked about this, okay? But basically what an imaginary solution is. So we know, well, first thing I want to talk about with these imaginary things. So we always know that there's going to be two. They're going to come in pairs, okay? The reason for that is anytime I do that quadratic formula and I get an I back out, right? Because that's usually whenever we end up with these, we always have like that plus or minus, right? Let's just say 2 plus or minus I over 2, okay? That would be, for instance, an imaginary root, but I know that there's actually 2 of them. That would be 2 plus I over 2 and 2 minus I over 2. So I know for a fact that these are going to come in pairs, okay? So don't let that scare you. Just know that there's never just going to be one, which means that, for me, I can go ahead and know that these are always going to have a multiplicity of even, right? There's always going to be at least 2, and they're coming in pairs, so these are always going to bounce, okay? The kicker, though, is that since they're an imaginary solution, they're not technically an intercept, right? They are, but they're not, okay? They're not an x-intercept. So they're not really going to go through the x-axis, but they're just going to bounce in a different place, okay? So let me show you what I mean by this. So we'll just work our way left to right and just using what we do know about these, okay? So we know we are starting upwards, so I'm going to come on in here. My first root's going to be at -1, and I know I'm going to bounce -1. So here I go. I just bounced it. I know I'm going through my root at 0, so I'm going to go ahead and go through this line. I'm going through my root at 5. I don't know how far down to go, but here I am. Okay, normally I just go ahead and finish this graph off by connecting that arrow to this, but I have imaginary roots. I know that they're not going to be on the x-axis because I'm already crossed this line, okay? But what I need to do is I just need to go ahead and like bounce, okay? It doesn't have to be perfect. These look really, really bad, okay? Mine looks really, really bad. Yours might look a little different than mine. But basically, when I'm grading this, I need to know that you understand these concepts, okay? So even if you only went like this far down, maybe, okay? You didn't go as far down as I did here, that's fine, okay? Our graphs don't have to look identical, just as long as you get the gist of what's going on, okay? If your bounce was way bigger than mine or smaller, that's okay too, okay? These don't have to be 100% accurate. It's just relatively speaking, okay? So now what I want you to do is I want you to go ahead and try 2 and 3. Use that chart if you need it, okay? And then we'll go over these and we'll keep going along. Okay, so first off, we had our odd degree and our negative leading coefficient. So what you should have found for your arrows is that we, to the left, are going up, and to the right, we are falling, we're going down, okay? We've got 2 imaginary solutions coming first. Then we have a root at 0 with a multiplicity of 2, which is going to be a bounce, which actually the imaginary is going to be a bounce too, okay? And then we've got a real root at 5 with a multiplicity of 3, which means it's going to be a through, because 3 is odd. So I'm going to go ahead and put the roots down that I know, which are 0 and 5. And now we're going to go ahead and draw this. So I know I need to have a bounce before I get to that root at 0. So whatever your bounce look like, I don't care, okay? But then we're going to go ahead and bounce 0, and we're going through 5. So it should look something like this. My arrow down there looks a little funky, so there we go. Okay, next up we've got an odd degree and a positive leading coefficient. So what that means is that we're going to start going down and going up, okay? And then we've got 4 real roots, so that's nice. And if I look, I've got one at -4, I've got one at -2, I've got one at 0, and I've got one at 3. If my multiplicities are odd numbers, we're going through, and if it's even, we're bouncing. So I'm going to start off, I'm going through my first 3 roots, so 1, 2, 3, and then I'm bouncing that last one. So it should look something like that. All right, next up, we have just answering some questions based on the graph that they've already given me, which is cool. So now I don't have to graph it, I just got to answer the questions. So if I look, the first one says, is the degree 3 or 4? So we talked about however many times it possibly crosses the x-axis, okay? That could be its degree. And if we look, this one actually looks like it crosses 3 times, and it does. But if we notice, this one's a bounce, so technically that's 2 roots. Okay, so that's where they try to trick you. Honestly, the easiest thing for me, instead of looking at where it crosses the x-axis on these, is just looking at the end behavior, okay? So if I know that I'm going up when I'm going left and up when I'm going right, or rising both directions, if I look back at my chart, I know that that means a positive leading coefficient and an even degree. Which one of those is even? 4. Okay. But then we want to know how many real roots, okay? And this one, I would take 3 or 4, because technically 1, 2, 3, right? And you could argue with me and say that, okay, yeah, that has a multiplicity of 2, but technically it's the same number, okay? But technically it's also 2 roots. So I would put 4. If you put 3, I wouldn't count it wrong, but just know that one of them does have a multiplicity law with it, okay? Then it says name each real root and state if the multiplicity is 1 or 2. Okay, so this is where you'd probably catch yourself if you did not notice that. So if I look here, I'm going to erase these just so I can see these numbers. So I do have 1 root here at -2, when x is -2, and the multiplicity is 1 because it's going through it. I have another one at x equals 0. It's also going through it, so it's also a multiplicity of 1. And then I have one at x equals 2, and we can see that that's a bounce. So we'll call it a multiplicity of 2. Technically, it could be 4, 6, 8, right? Because those are also even numbers, and those would also be bounces, but whatever you want to put there, I've just put 2. Are there any imaginary complex roots? So are there any other bounces that are not accounted for? I don't really see any here. Okay? And then it says circle any points that appear to be a relative max or a min, and then label them. So technically, I would call this one a relative minimum, right, because it's low. And this would actually be the relative maximum. And that's it for that. So I want you to go ahead and pause, and I want you to try that in the next one. So if we look here, is the degree 3 or 4? Well, hopefully you remember graphing those cubics, and cubics are always x to the 3rd, so that one is 3. How many real roots does this one have? So how many times does this one cross the x-axis? Only 1 time. Name each real root and state if the multiplicity is 1 or 2. So if we look, I'm going to call that like -1.5, and the multiplicity would just be 1 time because it goes through it. Any bumps happening here? You see this one? So technically that is a bump, okay? So we're going to call that imaginary. We don't know what it is, and that's okay. We're just going to say yes. And then do I have any maximum or minimum points? Technically no, okay? Technically this one's going left, right, up, and down in all directions, and technically this little flat part here that it kind of levels out, that's not a high point or a low point because we don't really know what this is doing exactly. So we're just going to call that a no. Okay? Alright, putting everything together. So graphing it all, we've seen these lines before. We know what they mean, okay? So domain, this one we can see, it's going left forever, right forever. Range, so from bottom to top, my lowest point is right here, and the y value on that is -1.31, it looks like, and then we know that this is going up forever. We know that we rewrite our domain as our approaches here, so -infinity, +infinity. As we approach to the left towards -infinity, as x goes left, where's y going? Up. So y is approaching infinity. And as x goes to the right, where is y going now? Also going up forever. So this one is going to be infinity for both. And now we look, do we have some max and min points? And it looks like we do. So technically what would be, we'll start with max, what would be our highest point, relatively speaking? And hopefully you said this one right here. So 0, 0.301 and 1.238. Okay, and then we've got our minimum point. So we can see that there's 2 points here, but technically this one's lower, so that's the one I'm going to write down. Okay. Increasing, decreasing interval. So these are the same thing that we've talked about before with our quadratics, but we're just going to have them be a little bit longer here. So if we look, let's say we have Miss Browning here, and she's running, even though she doesn't really love running that much. So technically, I'm going down to that turning point there, and then I start to go up. So my first little interval there from negative infinity to this x value of that point, so to negative 0.778, technically I'm decreasing, okay? Now we'll look, now I start to increase to this point, okay, and that is from where I left off, so negative 0.778 to the x value here, 0.301, I am increasing. Had a turning point though, and now I am running downhill again. So from where I left off, I'm decreasing. So from 0.301 to the x value here, which is 1.603. And then my turning point, I start to go back uphill to infinity. So we'll go ahead and put a U shape here from that x value where I left off, which was 1.601 to infinity. Is my increasing interval. Okay, so once we've got that taken care of, now we can just look back at this graph and see where do I cross the x and y intercepts. I don't have to solve for these, which is good. I just need to look. So we'll start with x. Looks like 1, 2, 3, 4 points, and they've given me all of them. So I just need to write them down. Negative 1, 0, negative 0.50, 1, 0, 2, 0. And then my y-axis looks like I just have 1. 0, 1. And that is it for those. So make sure you got that down. Pause this video if you need more time to write that down. And I want you to go ahead and try example 2. And that is the last one for today. So looking here, looks like we've got a cubic function. So hopefully for the domain, you did negative infinity to infinity. Range was also negative infinity to positive infinity on this. So that's our y-axis. We're going up and down forever. Rewrite our approaches here, okay? And now we look as a bird is flying to the left, or as x approaches negative infinity, y is going down to negative infinity as well. Same thing for going to the right, y is going up, okay? Positive infinity there. Now we look, so even though this is a cubic, do we have max and min points? Yes, we do. Hopefully you put this point right here as your max, because that's the highest. So that would be negative 0.549, comma, 0.631, I'm running out of room. Our minimum point then is going to be 1.215 and negative 2.113. Okay. Now we've got our intervals. So we'll start running here. First one is going to obviously be increasing. Okay. So from negative infinity to this x value. So negative 0.549. That's increasing. Now we switch, we are now decreasing from that point, so from negative 0.549 to this x value, 1.215. And now, finally, looks like we just had one more turning point, and we're now increasing. So we'll put a U shape here. We left off at 1.215, and we're going to infinity. And now I'm going to clean this back up, and we'll look for our x and y intercepts, and then we'll be done. So if we look, x-intercepts 1, 2, 3, and they gave them to me, so negative 1, 0, 0, 0, 2, 0. And y-intercepts, looks like we just have 0, 0. And that is it for today. Okay, so please, please, please make sure that if you are confused, if you have any questions at all, please go ask any math teacher in this hallway, okay? Don't wait for me to get back from my trip, okay? Because I don't want you to be super confused when I get back and then have to take this final. So please, please, please go get help and go ask questions. They all are here for you, okay? Don't message me on Canvas because I won't get it until I get back, okay? So please, please, please make sure if you need help, you ask a friend that knows what they're doing, or you go ask a teacher in this hallway, a math teacher, okay? Thank you guys, and I will see you soon.